Hello everybody, my name is Ataka. I'm from Queen Mary University of London. So today I would like to present my research titled Observer-Based Control of Inflatable Robot with Variable Stiffness. So I would like to start with some advance in soft robotics in recent years. So we have seen a lot of development in the field of soft robotics nowadays. So we have seen example of soft robotics from silicon, like stiff lock manipulator, being employed in a surgical environment. So the flexibility of the robot makes this type of robot very good candidate to be used in a cluttered environment. And we can also see some example of other soft robots such as arm manipulator and also the Festos bionic handling assistance. Despite this advance in soft robotics, in general, they still have one big problem, which is they have very limited payload capability because of the softness of the materials that they're using. So, and normally they don't have a capability to change this softness or stiffness of the robot body in order to solve this problem. That's why in recent years, there have been research which try to tackle this problem by proposing a stiffness controllable soft robot. So one example here is from my colleague at King's College London. They use the combinations of antagonistic principle between tendons and pressure in order to be able to change the stiffness or softness of these materials that is being employed as soft robots. So the robot is able not only to maneuver, but also to modify its stiffness. Also, another example of application here is this growing robots from Professor Okamura, which is able to not only create a bending, but also able to grow basically. Besides also able to control the stiffness of the robot body, as can be seen here. However, this type of robot, despite having an ability to control their stiffness and therefore they're able to basically improve the payload capability, they still need to quite complicated control architecture, because then we need to control not only the pose of the robot but also the stiffness of the robot, right? So that's why in our previous work this year in ICRA 2020, we presented a model-based pose control for this type of robots, inflatable robot, we call it, with variable stiffness. So the idea here is we try to develop a model from an experiment to develop a relation between the pressure given to the robots as function of the robot's tip positions. And in doing that, we also consider the effect of pressure that is going into the main chamber of the robot that will affect the stiffness of the robot. So in this video here, regardless of the stiffness of the robot's tip will be able to actually follow the same trajectory. So this is our most recent results. However, this proposed algorithm also has problem because in that paper, the model that we use to control the robot is created offline. So now in this work, we will try to actually solve this problem by trying to do an online parameter estimation to model the robot's bending capability. Right, so I will start with the model of the robot. So we have a bending model here. Basically, the robot is created from fabric. So basically here the fabric, so in the fabric itself, in the surface of the fabric, we attach inflatable pouches. So in this form, so when it's deflated, it's basically straight like this, flat, straight surface. But when we inflate these pouches, it will form a cylindrical shape like this one, and hence this will create a contraction, and this contraction will decrease the overall length of these pouches. So if we inflate one pouch at one time and deflate the other pouch at the same time, this will actually create a bending movement like shown in this figure. So this bending angle will be affected by basically two factors. The first one is the main chamber inflation pressure P0, is the pressure that goes into this main chamber of the robot. So the higher the pressure, the stiffer the robot becomes, and the smaller the bending angle. So yeah, besides the main chamber inflation pressure, it will also be affected by the pouches pressure PI, which is given to these pouches. So here in our model that is also used in our previous paper, we have several assumptions. So first of all, we assume that the tension created by these pouches is actually proportional to the pressure. And then we also assume that each section, so here in this image, we have actually 3 sections of the robot, 1, 2, and 3. So each section will behave like a constant curvature. So this will be like an arc of the circle. So then the curvature will be proportional to the bending moment as given by this equation here. However, not only we don't stop here, but we try to actually calculate or take into account the effect of the inflation pressure into the robot's bending model. So this is the standard model, which can be found in the literature. However, here now we modify this rigidity constant E. We replace this parameter with this term, which is the summation of the Young modulus E and also the effect of the inflation pressure P. And now we can actually map the pressure of the pouches, the pressure of the main chamber into the bending angle produced by the robot. Right, so once we know this model, we can actually map the actuator space into the configuration spaces, which is basically the angle of the robot. And because we assume a constant curvature from geometry, we can actually transform this angle, bending angles for every sections, into the position and orientation of the robot, from which we can then calculate the Jacobian, which can then be used to control the robot's movement. One contribution that we made here in comparison to the previous paper is the online parameter estimation. So here now we have the bending equations, we have the input to the robot, which consists of the pressure to the main chamber and to the pouches, and then we have the output, which is the bending angle. So this is the states, we actually reformulate the equation to become a state space model, and then we use this state space model to help us estimate these parameters. So basically the C1 and C2 for every segment. So if we have n segment, we have basically 2 times n parameters that needs to be estimated. So yeah, basically we try to estimate these parameters, and then the idea is to use this estimation to calculate or to estimate the Jacobian of the robot that will be used in the control part. However, as we can see here, the equation is actually a nonlinear equation. So if we have this nonlinear equation, in order to correctly estimate all these parameters, we actually need to provide the robot with a persistently exciting input. Basically, we cannot give like monotonous signal and expect the model to be, or the parameter to be estimated straight away because of the nonlinearity in the model. So that's why instead of estimating these parameters, we actually estimate this constant B, which is a function of these parameters, this estimated parameter. And actually from this constant B, we can calculate the Jacobian straight away. So we're gonna see here that the Jacobian is actually linearly related to these constants B's for every segment. That's why we're gonna see that we don't need to correctly estimate these parameters in order to correctly estimate the Jacobian. We just need to make sure that this B parameter is correctly estimated, then the Jacobian will be automatically estimated. So we're gonna see that using the extended Kalman filter, and we can calculate or estimate the Jacobian based on the information that we have, which is the input that we give to the robot and the output that we measure using the sensor. Right, so once we've got the Jacobian information or Jacobian estimation, we can then use this to employ inverse Jacobian technique to basically control the robot's tip and orientation, robot tip's position and orientation. So we're gonna use RGBD camera attached on top of the robot to detect this bending angle theta for every segment. So the idea is to use markers here in the robot body. We're gonna show the markers in the video. And from this marker, we're gonna estimate the bending angle. And using this bending angle and the pressure information that we give to the robot, we then estimate the Jacobian and then calculate the control signal that we need to give to the robot in order to achieve some trajectory. Right, so this is some of the results that we have in the simulation environment. We can see here that we start by giving some arbitrary value to the pressure of the main chamber and pressure of the pouches. And then that's when the estimation process started. So here the estimation process started. And then we can see here, this is the parameter of the 3 sections of the robot. So this is the first section, second section, and third section. For each section, we have 2 parameters, C1 and C2. And we can see here that the parameter estimation is actually not correct. So there is this error here between the estimated value and the real value that we give to the robot. However, we can see here the parameter B's that is related to the bending parameter C here is actually so the estimation is actually correct. So we can see here the dashed line is the estimation and the solid line is the real value. And we can see here right from the beginning the estimated value go to reach the real value of the parameters. So from here we can actually conclude that actually the Jacobian will not depend, the Jacobian estimation will not depend on the correctness of the bending parameter estimation. So we can see here as well the error Jacobian. We can see like from the very beginning the error Jacobian goes to 0, meaning that the Jacobian can be estimated correctly from the beginning of the experiment. And then after that, after some time, we order the robot to follow some trajectory, which is the straight line trajectory. We can see here that the tip of the robot is able to follow this desired trajectory. And then after that, we try to improve or increase the stiffness of the robot. Here, the red line is the pressure. Once we increase the stiffness of the robot, we can see here that the trajectory tracking and the parameter estimation is not affected at all. So we have actually more results, but I would like to invite you to take a look at the paper to see more result of the simulation section. And now let's turn into the experimental section. So here we show some videos of the experiments that we did in our lab. So we implemented the control algorithm in this robot. So here we can see that we have several markers on the robot body, the red marker, the red points, and we use this marker to estimate the bending angle of each sections. Apart from that, we also use this marker to detect the tips. So the goal is movable. We can control the goal position from keyboard, and we can see here now. So this one using 0.3 bar pressure, meaning that the robot has a very low stiffness, and the position control already starts. So from this position into this position. However, we can see that there is actually a steady state error here. Because here we have emphasized on the safety of the robot. So when the robot is in the low stiffness, the safety and flexibility becomes the priority. So in that case, the robot will have bigger steady state error because it doesn't have enough stiffness to work against the friction in order to move towards this target, in order to eliminate the steady state error, right? However, in this case, the robot will be more flexible and safer. So now we try to increase the stiffness of the robot. So, and also to move the goal or the targets towards another arbitrary positions. So now the position control restart. So now we are using the medium pressure, 0.6 bar, medium stiffness, and we can see that the robot can go towards the target as well. And this time it has a lower steady state error. So now the position control behaves better in terms of the steady state error, but the robot becomes more rigid, meaning it's become less flexible. And finally, we try also to move the target to the third locations and increase the stiffness of the robot to be very high. And now, so 0.95 bar, and now the robot is able to reach the target immediately. And yes, and it has very low steady state error, right? So now we show that the proposed observer-based force control can be used to control the inflatable immersion robot under various stiffness conditions. In achieving this performance, the model parameters doesn't need to be identified offline. So now the model parameter can be identified online using the extended Kalman filter, and then we can use this information to estimate the robot Jacobian used in the control scheme. And finally, in the future, we're going to try to explore the use of more advanced models, the use of more advanced estimation and control algorithm, and finally to study the interaction between the robot and the environment. Thank you very much.